Hi class, how are you? Today we are going to discuss file organization. Of course, in file organization, we are going to look at how records are stored on the disk. And then we shall also look at how these records can be accessed from the disk. So the objectives of this class, one is at the end of this lesson, we should be able to explain storage devices, characteristics, and also be in position to discuss file organization. What is a file? A file is a collection of or a log of records. So you have a file that has different records. And remember that each and every particular record has fields. Remember, a field is an attribute. So those records are, each and every particular record has fields. So these records are mapped onto the disk blocks. Okay, each and every particular record that you have is put onto the disk block, and then of course the disk block is comprised of different pages. So in a relational database, there are files of fixed length record, and then also we have files that have variable length. In other words, we have files that have files whose records are fixed in terms of bytes, and then we have files that records that vary from one record, and they are from one record to the other. Many of the techniques used for the former, in other words, the techniques that are used in the fixed length record can be applied to the variable length. Thus, we begin by considering the files of fixed length record. So when we are talking of files of fixed length record, what exactly are we talking about? Sorry about that. So let's just take an example, okay? As an example, let us consider a record from a bank database. Now, if you look at this record in pseudocode, the record is a deposit record. This record has account number as one of the attributes, which is the char data type, and it has 10 as the attribute domain. Then it has the branch number, which is also char data type with 22 as an attribute domain or the size. And then it has the balance numeric, which has 12 and 2. So if you look at that record, okay, with those fields or those particular attributes, so we assume that each character occupies 1 byte. So in essence, here we're saying that we've said that the account number has 10 characters, the maximum of 10 characters. So we're saying that we are assuming that each of these characters is equivalent to 1 byte. And that this numeric, of course, is 12 plus 2. And then for this particular numeric, we are saying that let it occupy 8 bytes. Let us assume that it is occupying 8 bytes. And then at the end of the day, our account record is going to be 40 bytes, 40 byte long. The 40 bytes, where are they coming from? They're coming from the 10 plus the 22, okay? This 10 plus 22 plus the 8 that we said that we are assuming that this 12, the balanced numeric has an equivalent of 8. So in essence, that particular record is equal to 40 bytes. So it's 10 plus 12 plus 8. So a simple approach is to use these first 40 bytes for the first record. So that is, we are assuming that that record is 40 bytes. So we take them to be the ones that we're going to use for the first record. So the next 40 bytes for the second record, and so on and so forth. So this is what we refer to as a fixed length. It would mean that each and every particular record in your file is going to have exactly 40 bytes, and that is what we refer to as the fixed record. The challenge with this kind of approach is, one, that it is very difficult, okay, to delete a record from this structure. Why? Because the space occupied by the record to be deleted must be filled with some other record of the file, or we must have a way of marking the deleted record so that they can be ignored. So for example, we can see this in let's look at this example here. So we're saying that we have said that it's very hard to delete. Okay, it's very difficult to delete a record of the structure. The space occupied by the record to be deleted must be filled with some other record of the file, or we must have a way of marking this deleted record. So in essence, this is what you're saying, that you are assuming that this is the what? We are assuming that this is our file. This file has record 1, record 2, and record 3. These are the records. So we're saying that in the event that you're going to delete this record, okay, it becomes very hard to, because it would essentially mean that you have to first replace this record, okay, that we have deleted. Otherwise, you need to have what we call a deletion marker, such that we can such that we can be in position to know that there is space that still exists in this file by use of a deletion marker. So that is the challenge of having a fixed length record. So that's what you're saying, that either you have to have a way of marking these deleted records. Otherwise, it becomes very hard for you to keep track of the space of where that particular record was. So we're saying that unless the block size happens to be a multiple of 40, so we'll have what you call a block. A block has different pages, okay, within it. So in the fixed length records, we're saying that each and every particular record has a standard of 40. So we're saying that the disadvantage this thing has, that unless the block size is in a multiples of 40, which in most cases is unlikely, some of the records will have to cross block boundaries. So in essence is, if you have, okay, a particular record that is more than 40 in size, it means that it will not be able to fit on this what? It will not be able to fit on this block, because this assumes that each and every particular record is 40, but it may not be the case, okay? So what does that mean? It means that if you have a record that is more than 40 characters, then the storage will have to not only leave, it will have to leave that block, and then also store that record store part of that record or the remaining record in another block. And of course, why is that not so good? Because then it increases on what we call block accesses. Block accesses, yeah, for example, if you request for a particular record, if your blocks are many, it means that it kind of also affects the performance, because the system will have to look through all those particular blocks to identify that particular record. So the more the blocks, the more tedious the accessing of the files or records on that block becomes. So we are saying, so in essence, we are saying that it would thus require 2 block accesses to read or write such a particular record. And of course, the disadvantage of that is the performance, that means if you're going to look for a particular record, in the time that you take to look for a record in 1 block is different from the time if you're going to look for a particular record in 2 blocks or even 3 blocks. So that is where the performance comes in. Okay. All right. So this is just the explanation, the further explanation. So when a record is deleted, it's undesirable to move the record to occupy the space freed by the deleted record, since doing so requires additional block accesses. So this is what I'm saying, that in the other demonstration that I had, we're saying that it is not the best approach. It is not what is desirable for you to move the records to occupy the space that was left as a result of deleting the record. Why? Because it is going to increase on the block accesses. So in essence, this is what I am referring to. So if we delete this record, okay, what we're saying that it is not advisable for you to occupy, it's not advisable for a new record that is going to be inserted in the block to occupy this space. Okay, that is what we're saying. It's not desirable, because then it is going to increase on the block accesses, the number of blocks that will be used to search for a record, or even to retrieve a record. So it would mean that you're going to increase on the number of blocks if you're going to use that particular approach. So that is the statement, that when a record is deleted, it is undesirable to move the records to occupy. So it's not a best practice to move the records to occupy the space that has been deleted, because it would increase on the block accesses. So since insertions tend to be, we're saying that in a database, generally, insertions tend to be more frequent than the deletions, okay? So it is acceptable, first leave that space, okay, that was occupied by the deleted record, and you wait for a subsequent insertion before reusing the space. So in essence, we're saying that it is better to leave the space for that particular record, okay? Leave it, but don't move Don't move the records to fill that space. So you can leave it, because we know that usually insertions are more frequent in the database. So at a given time when you're going to insert data, then the data the row that you're going to insert can use that space that has been freed by a deleted record. So a simple marker on the deleted record is not sufficient, okay, since it is hard to find this available space when an insertion is being done. So in other words, by just using a simple marker, okay, on the deleted record, like a deletion marker, it is not enough. Why? Because it is very hard to identify that available space at the time when the insertion is being done. So that is why we're saying we need to introduce an additional structure such that insertion to that particular file becomes a little bit easier. Okay, so and this is what we're now, the additional structure is what we're going to look at, and this is what we this is we commonly use what we call file headers. So we're saying at the beginning of the file, we allocate a certain number of bytes as a file header. The header will contain a variety of information about the file. So the header contains quite a number of information. It can contain information about the free spaces on that particular, the free spaces in the page. It can also enable us to know the spaces that have been occupied on that particular page. And then it can also have the address of the deleted records, and so on and so forth. So for now, all we need to store there is the address of the first record whose contents are deleted. So it's going to have the address of the record that was deleted. So then we use this first record to store the addresses of the subsequent records. So it will store the records of the second available record, and then the third and the fourth and the fifth. In other words, for each and every particular record that has been deleted, an address is going to be stored in the file header. the address of the deleted record is going to be stored in the file header. Why do we need this? Because at the point of insertion, when you're inserting a new record, then we use the address of the deleted record to allocate the space, to find out the free space that was left by a deleted record, such that we insert our new records there. So intuitively, we can think of these stored addresses as pointers, since they point to the location of a record. The deleted records thus form what we call a linked list, which is often referred to also as a free list. So that means that all the records that you have deleted from your file will create what we call a linked list. So what is a linked list? A linked list. Okay, so take this as an example. Okay, you have this particular page. Okay, this page has a free page list indicating the pages that are free, that don't have data, and then also it has the page the data page list, the list of the pages that have data on. So we're saying that a linked list maintains a header page at the beginning of the file that stores two pointers. The first pointer is it stores the head of a free page list, that is, it has a header of the pages that are free. Then it has a header of the pages that have data. So in essence, you have something like this. This is your page. So you have a header, this header for the free page list. In other words, it points us to the pages that are free. And then you have a header that points us to the pages that have data on. Okay. So each page keeps track of the number of free slots in itself. So what happens is you will have many pages. This is an example of a page. You will have another page and another page and another page. So for each and every particular page, it will keep track of the number of free slots in itself that it has. So this is a continuation of the linked list. So then if you look at this example, okay, this one is now a linked list with many pages. So you have the header for the free page list, and then you have a header for the data page list. Okay, so if you look at these now, these are the different pages that are going to be pointed to either the free page list or the data page list. So you have this page, you have this page, you have this page, you have this page. This page has this page has the free page list. It has pages for data, this free page, data, and so on and so forth. Okay, so now when you are looking for, let's say, pages that are free, so this header will connect to this page, look for the pages that are free. If they are not there, it will connect to the other page. If it is not there, it will connect to, so the process continues. Okay, now this is when it is looking for data for pages that are free. Then you have this page that has data, this header that has pages that have data. So that means even when it is looking for, let's say, you're retrieving records, now this is where it will go to retrieve the records, because now these are the pages that have the records. So it will come in here, look for the pages. If the record is not there, it will go to the other record, look for the page, it will go to the other page, look for the records. If it is not there, the list continues. But remember that these arrows have to what? They have to go back. Because remember, it's kind of a loop. it has to go back. So if it is wherever the record is for example, whichever page where if there's a page where we'll find the free slot, then it has to go back, and then it has to go back, and then it has to go back. Same thing here. When the page comes and then there's one that has a free slot, where for example, if we have found our record in a particular page, it will come back, and then we come back up to the main page. So this is what referred to as a linked list. Okay, so within this file, you want to see which pages are free and which ones have data. So in the header of this heaped file of the linked list, which we saw initially, there are 2 pointers. One with the list of free pages and the other with the list of pages that have the data. So on insertion of a new record, we use the record pointer but we use the record pointed to by the header. We change the header pointer to point to the next available record, and then if there's no space available, we add the new record to the end of the file. So in other words, if you want to insert a new record, you keep looking you go in the free pages and you keep looking for a free slot. If all the slots have been taken or they're not available, then that new record is going to be added at the end of the file. So insertion and deletion of files of fixed length are very simple to implement because the space made available by the deleted record, that means the record that you deleted is going to be the exact space that we need to insert a record. So if we allow records of variable length in other words, if you have a page that is dealing with fixed records. Now, if you're going to allow records that have variable length, then this match no longer holds. That may no longer hold. That's why we said that now if you're going to include records of variable length, then that means they'll have to span to other blocks because the size of the records might be larger than the size of the disk. So this takes us to the variable length records. Okay, I'm trying to move this. Now, variable length records arise in the databases in several ways. One, storage of multiple record types in a file. That is, if you have multiple record types, you could have records that have different domain name, can have records that can have different, for example, fields that will contain different data. Then record types that allow repeating fields like arrays, okay, and then also record types that allow variable length for one or more fields. So in other words, where you're going to have different length of the fields within the same record. So we have different techniques for implementing the variable length records, and the most commonly used kind of technique is what we refer to as the slotted page structure. So the slotted page structure is used to handle records of variable length, and they are used to organize these records within a block. So there is a header at the beginning. So I need to move this a little bit. Okay, so there's this slotted page has a header at the beginning of each block. What does this header have? This header has one, the number of record entries in the header. It has the end of a free space to the block, that same header. Then it has the array of entries that contain the location and the size of each record. We are going to see how. and that record has the number of used slots. It shows us the number of used slots. So this, and at the end of the day, we are in position to know the number of slots that are still available. So that header of that particular slotted page has what we call a slot array. Okay, this slot array tries to map the slots of the tuples to the starting position offset. So that is what a slotted page is about. We are going to see it in our next slide, what exactly it is. So the actual records are allocated contiguously on the block. In other words, there's no specific way we allocate these records. That is starting from the end of the block. At the end of the block, that is where we start to allocate our fields, our records. So the free space in the block is contiguous, that is between the final entry in the header array and the first record. We're going to see that. So if a record is inserted, the space is allocated for it at the end of the free space, and an entry containing its size and location is added to the header. So in essence, let me just dive into the actual illustration to make this explanation a little bit easier for me. Okay, so this is what I managed to draw just to see if it can make sense to you. That's what I drew. So we have said you have this page, it has the header. Okay, so that is the header. This one is referred to as the slot array. So we have said that the slot array maps each and every particular slot to the tuple starting position offsets. So we have this slot array. You see, this is the first. This is the first slot, and it is corresponding to tuple 1. Okay, that is record 1. Then you have a second tuple. This is the second slot in the array that corresponds to this particular tuple. And then you have the third slot that corresponds to the third tuple. And then also you have the fourth slot that corresponds to the fourth tuple. So in this slotted page, okay, kind of page layout or assigning of records on the disk, each and every particular tuple, okay, is allocated, is inserted onto the page or allocated space, and then the header, which you have talked about, will store the information of the table that has been inserted on the page. So here these variables are both of fixed and variable length. So in this slotted page, it does not matter whether the variables are fixed or the variables are of different, they are of different size. So, so now we're saying that the slot array maps the slots of the tuple starting position offset. We have seen that. And how to fill the page. So the slot array is going to grow from the beginning to the end. So in other words, the slot array starts from here. It starts to grow from the beginning up to the end. And the data is growing. Now this data here, the tables that we are adding to the page, they grow, and the data is going to grow from the end, that is from the end to the beginning, so that we're going to start from this side going this side, whereas the slots start from the beginning up to the end. So at some point it will reach the middle, and we cannot store on this particular page any more data. So at that point the page is full. That is with the slotted pages. Okay, I hope it makes sense and it's understandable. Okay, so quickly So fixed length records can be easily allocated to blocks because they have fixed length. And then in variable length record, we need to find out the exact size of the record before allocating it to a block because because the size of the records keep varying. So it's also apparent that programs that process files of variable length will be more complex than those that are processing files that have fixed length, where the starting position and the size of each of the records is known. Why the ones for variable length are complex? Because the sizes of the length vary. So allocating the records to blocks. Now, the records of a file must be allocated to a disk block because a block is the unit of data transfer between the disk and the memory. So this is what happens. If, for example, I am looking for a particular record in a file, okay, or in a page, so what happens is the file, okay, is going to be the block that we presumably think has the record is going to be copied to the main memory. Okay, so that memory is going to read or scan through that particular block to look out for the record. If the record is there, the record is going to be displayed. But if the record is not there, that block is going to be taken. We are going to get another block from the disk. That is, the disk is the secondary storage. Another block is going to be gotten from the disk, copied to the main memory, and then we start searching for the record through the buffer. If the record is there, then that particular record is going to be displayed. If you're going to insert, it's going to be, if you want to insert a record, the record will be inserted on the block and then copied back to the disk. If you're going to change or we're going to modify the record after allocating the space for where the record is going to be, the record will be written onto the block and then taken back to the disk. So this essentially, that's what I'm trying to explain, that the records of a file must be allocated to the disk blocks because each and every particular record has got to be housed on the disk block, sorry, not on the disk block. So the actual block itself is the one that has the data. And whenever you want to look for data, the block is going to be copied to the main memory from the disk to the main memory, and then searches are done to that particular block. If the record is there, it will be displayed. If the record is not there, then another block is going to be picked from the disk, copied to the main memory, and then the search is done. So that is basically what happens. So when the record size is smaller than the block size, a block can accommodate many such records. In other words, if you have very small records, then that means the block can have as many records as it can handle. If a record has too large size, then a size to be fitted in one block, it means that you may have to use more than 1 or 2 blocks for you to have that record stored on the block. So the number of records on the block depends on the block size. Okay, the number of records that you're going to store on your record, the number of records that you're going to store on the block will depend on how big the block is, and then it will also depend on the size of the records. If the record size is small, that means you will have many records on the block. If the block size is big, that means you'll have many records on the block, and the reverse is true. So suppose the size of the block is B bytes, that is the size of the block is B bytes, and the file contains fixed length records of record R bytes. Then we can allocate BFR, okay? So what is BFR? BFR is the blocking factor for a file, which is the records in a file, okay? That is what we call the block factor. That is what we call the blocking factor. So the blocking factor is basically looking at the records in the block. So for you to get to know the records that are in the block using the blocking factor, it is the size of the block divided by the record, the size of the record. So we're saying that where x is the so-called flow function. So usually when you're saying where x is the flow function, that is for a fixed length record, we're saying that if, for example, you get 0.2, the answer is, let's say, 7.2. So we can round it off. We can use the flow function by looking at the integer that is next to the answer, but downwards. So in other words, you round off downwards. That is what we call the flow function. So in general, R may not divide B exactly, okay? So in other words, in general, the size of the record may not be divisible by the size of the block. So there that means that we shall have some leftovers in each block, which is equal to that formula. What am I saying? So if I am going to illustrate this, let me see how best I can illustrate this. We are saying that you can have this record, okay? No. Let's assume these are the records. So these records are on a particular block. So we are saying that sometimes, let me just say that now that one is a smaller record, especially if the records are of variable length. So let's just use this diagram as to show the different sizes of the records. So if you look at this makeup of these records, this one, let's assume that this one is 7 bytes, this one is 9 bytes, this one is 6 bytes, and this one is 5 bytes. It would mean that this particular block will have some unused spaces if we are taking tuple 2 to be, let's say, each, okay, let me do this. Hold on. Okay. Let's assume that, let's say tuple 1 is 9 bytes. So times 4. 9 bytes times 4. That is now 36. Okay. 36 bytes. This is just a hypothetical example. Now let us assume that this whole block is 36 bytes. The whole block is 36 bytes. But this one, okay, this tuple has only consumed, this tuple has 6 bytes. This tuple is equivalent to 9 bytes. This tuple is equivalent to 5 bytes. And this tuple is equivalent to 7 bytes. Now, when you add these bytes, this is 15, this is 20, and this is 27. That means that 27 bytes, okay, the records have only consumed 27 bytes. Yet the entire block is equivalent to 36 bytes. So that means there is some unused space in this particular block. And this unused space, how do you calculate it? You get the size of the block and you subtract BFR. Remember, we have said BFR, these records on the file, times the size of the record. The size of the record. So for you to know the remaining space or the leftover on that particular block, that is the equation. So let's take an example. They're saying that if the block size was 10B, the block size, and the size of the record was 3 bytes, how many records are present in the block? Okay, they're saying that hold on. Yeah, I need to open an Excel sheet. So they're saying that the block size is 10, so B is equal to 10. Then, and the record size is 3 bytes. And then they tell us how many records are present in the block. So the records that are present in the block, remember, that is the BFR. We have said that BFR, those are the records in the block. So BFR is equal to B divided by R, the size of the block, divided by the size of the record. So it is 10 divided by 3. And then you get 3.33. Okay, these are the records in the block. The records in the block. But we said that you employ a floor function, okay, which rounds off the value x down to the next integer. So in this case, we shall round up and we have 3. So this is the BFR for this particular instance. Okay, so if we do not want to waste the unused spaces in the blocks, we may choose to store the part of the record in them and the rest of the record in another block. So in other words, instead of leaving that space unused, you could consider storing the record in one block, and then you also push that part of the record in another block. That kind of file organization is called expand file organization. So if records are not allowed to cross block boundaries, in other words, if you want to keep the records within one block without having to cross to another block, we call it unspanned. So unspanned organization is useful for fixed length records with the length of the record known, and the size of the block also is known. So it makes each record start at a known location in the block, which simplifies record processing. But for variable length records, we are saying that the variable length can either be spanned or it can be unspanned. So it is normally advantageous to use spanning, because then you reduce on the wastage of space in the record rather than leaving some spaces unused. It is important that you use unspanned, such that you can fruitfully put your disk to full use. So for variable length records using spanned organization, each block may store a different number of records. In this case, the blocking factor represents the average number of records per block for the file. So we can then use BFR to calculate the number of blocks B needed to accommodate the files. Remember, the other B, the capital B, looks at the block size, but this one is the small b. The small b looks at the number of blocks that you need to store your records. Okay, that is the small b. And we are saying that for us to know the number of records that you will need to store the records on, especially where you have variable length, because you need to know the size of the block that you will need, because these are variable lengths, they are not fixed. So the equation is, it's R, okay, divided by BFR, the R. Now, the other big R was the record size, okay? They are the record size, in other words, the length of the record or the size of the record, that is the big R. And the small r is the number of records, okay, that can be stored on the file. So it is not difficult to see that if the record size R is bigger than the block size B, then a spanned organization has to be used. We are saying that if the size of the record, okay, a particular size of the record is bigger than the block size, then it is important we use the spanned. The spanned organization is where you have one record that spans into another block. File header. A file normally contains a file header or a file descriptor providing information which is needed by programs that access the file records, like the other file header that we had when I was explaining a slotted page. The contents of the file header contain information that can be used to determine the disk addresses of the file blocks, as well as the record format descriptions, which may include field length and the order of fields within the record, just like how I showed you in the slotted page. Okay, so to search for a record on the disk, one or more blocks are transferred into the main memory. Okay, into the main memory buffer. So the programs then search for the desired record and the records within the buffers using the header information, just like what I have been explaining. That is how, data is moved. So you get the blocks, one or two, depending on the type of search that you're going to use. It's copied into the main memory. Then the programs do a search of the desired records within the memory, within the buffer, using the header information. Remember that header has all the information that concerning the records. So if the addresses of the blocks that contain the desired record is not found, then the program have to carry out a linear search. A linear search is where you go on disk block by block, one block after the other, and going through each and every particular block, such that you do this. That's what we call a linear search. In terms of performance, it takes a lot of time, and also the terms of computing resources, because you have to go through all the blocks for you to get that particular record that you're looking out for. So each block is loaded into a buffer and then checked until either the record is found or all the blocks have been searched unsuccessfully. That is using a linear search. This can be very time consuming for a large file. So the goal of a good file organization is to locate the block that contains the desired record with a minimum number of block transfers. Minimum number of block transfers. That is now what we call that is now looking at efficiency. Okay, you want your database to be efficient. So the desirable state, what is the desirable state? The desirable state is, one, to make sure that you can locate the desired record in the shortest time possible, and going through a few block transfers without having to transfer all the blocks onto the main memory. That is the desired state. So operations on the file. Operations on the file. Operations on files can usually be grouped into retrieval and updates. The operations we mean as whatever we do on our file. It can be retrieving data from the database. It can be an update. An update can be in form of inserting, deleting, or modifying. So typically, a database management system can issue requests to carry out the following operations. These are some of the operations that can be done by the DBMS. Okay, there is what you call a find operation. There's a read. There's a find, next, delete, modify, insert. All those are some of the operations. For example, the find or locate, it searches for the first record satisfying a search condition. It transfers the block containing that record into the buffer. Then the record is located in the buffer and it becomes the current record, or it becomes ready to be processed. That is what we call a find or locate. So what you need to know basically when it comes to finding, when it comes to retrieval, updates and everything, one thing that has got to go at the back of your mind is one, that blocks are transferred to the main memory. Searches are done, updates are done, insertions are done, deletions or modifications are done, and then this block is taken back to the disk or the secondary memory. So the read or get, the copies the current record from the buffer to the program available. This command may also advance. So basically, you will look through all this. Okay, these are some of the operations that are done on a file. Find, next, deleting. So the same thing that happens if you're going to delete a particular record, the block is taken to the main memory, from the disk to the main memory, then a search is done, a record is got, and then the record is deleted, and then an update is done, and then back to the disk space. Modification is the same, and then also the insertion is the same. The same process in essence. Okay, so those are more file operations. Find ordered retrieval retrieves all the records in the file in a specified order. Reorganizing, etc. Okay, so there are two concepts must be clarified. There is what we call file organization, okay, which looks at the organization of data or the organization of records on the blocks or on the disks. That is file organization. But then also we have access methods, how we access the data on that disk. So those are two most common concepts that need to be clarified. And today we are looking at file organization. So we are saying that file organization, this concept generally refers to the organization of data into records, blocks, and access structures. It includes the way in which records and blocks are placed on the disk and how they are interlinked. So access structures are particularly important. They determine how records in a file are interlinked logically as well as physically, and therefore dictate how we shall be accessing those records in the file. So we have different access methods, okay? But access method, it consists of a set of programs that allow operations to be performed on a file, okay? We have the use of indexes. We have those helpers in, let's say, accessing files or accessing records using indexed files. So now we're going to look at how files are organized on the disk. We're going to discuss the three methods of file organization in the next part of the video.